Hello everyone. Welcome back to another warm and wonderful journey through physics. And yes, I mean literally warm. Have you ever noticed that when you leave a metal chair and a wooden chair out in the sun, the metal feels hotter even though both were under the same sunlight? Why? They absorbed the same heat energy, but their temperatures changed differently. That's where today's concept, specific heat capacity, comes into play. When we supply heat, represented by the symbol Q, to a body, its temperature increases depending on two things, its mass and the material it's made of. The amount of heat required to raise the temperature of 1 kilogram of a substance by 1 Kelvin is called its specific heat capacity, denoted by the symbol S. Mathematically, we say Q equals m multiplied by S multiplied by delta T. Here, Q is heat in joules, m is mass in kilograms, S is specific heat capacity in joule per kilogram per Kelvin, and delta T is the temperature rise in Kelvin. That's why water, for example, takes much longer to heat up than sand on a sunny beach. It has a higher specific heat, meaning it needs more energy to raise its temperature. As shown in the diagram, a calorimeter setup measures how much heat is absorbed or released, helping us determine the specific heat of materials accurately. Now let's zoom in a bit on gases and moles. Yes, it's time to meet the molar specific heat. Instead of talking about per kilogram, we can define specific heat per mole of a substance. The molar specific heat, represented by the symbol C, is the amount of heat required to raise the temperature of 1 mole of a substance by 1 Kelvin. So, the formula becomes Q equals N multiplied by C multiplied by delta T. Here, N is the number of moles, C is molar specific heat, and delta T is again the temperature change in Kelvin. There's also a relationship between specific heat and molar heat. C equals m multiplied by S, where m is the molar mass in kilograms per mole and S is the specific heat. For gases, we have two special cases, one at constant volume and one at constant pressure. We call them C sub V and C sub P respectively. At constant volume, no work is done by the gas, so all the heat goes into raising temperature. But at constant pressure, the gas expands, doing work on its surroundings, so C sub P is always greater than C sub V. As you will see in the PV diagram, the constant pressure line rises more gently than the constant volume one, illustrating this difference. Alright, time to get experimental. How do we actually measure specific heat? We use a process called calorimetry, based on one simple but powerful principle, the law of conservation of energy. When a hot body and a cold body are placed in contact, the heat lost by the hot body equals the heat gained by the cold body until both reach the same final temperature. The gunning equation is m1 multiplied by s1 multiplied by open bracket t1 minus t close bracket equals m2 multiplied by s2 multiplied by open bracket t minus t2 close bracket. Here, m1 and s1 are the mass and specific heat of the hot body, m2 and s2 belong to the cold body, t1 and t2 are their initial temperatures, and t is the final equilibrium temperature. To minimize heat loss, we perform this experiment using a calorimeter, a highly insulated copper container, often with a thermometer, stirrer, and known water equivalent to account for the container's own heat absorption. As shown in the figure, the calorimeter ensures that almost all heat exchange happens only between the sample and the water, giving us an accurate value of specific heat. Now let's see how specific heat changes across substances and why it's so important in nature and technology. Specific heat depends on material type, temperature, and state of matter. For instance, metals have relatively low specific heat, so they heat up quickly, while liquids like water have very high values. Let's take an example, The specific heat of water is 4186 joules per kilogram per Kelvin, while that of copper is only 390 joules per kilogram per Kelvin. That's why your copper pan gets hot in seconds, but the water inside it takes time to boil. Copper has a low specific heat and water has a high one. Substances with large specific heat resist temperature changes. They're nature's thermal stabilizers. That's why coastal regions, surrounded by oceans, experience milder temperatures. The water absorbs and releases heat slowly. On the other hand, materials with small specific heat, like sand or metal, change temperature rapidly. That's why deserts get scorching hot in the day and freezing cold at night. As you can see in the bar graph, the contrast between metals and water is enormous. Water's high specific heat makes it an ideal coolant in car radiators and industrial systems. Let's apply our formula to a simple numerical example. Suppose we have a copper block of mass 500 grams, which is 0.5 kilograms. Its specific heat capacity is 390 joules per kilogram per Kelvin, and its temperature rises from 20 degrees Celsius to 60 degrees Celsius, a change of 40 kelvins. We need to find how much heat the copper block absorbed. The formula is Q equals M multiplied by S multiplied by delta T. Substituting the values, Q equals 0.5 multiplied by 390 multiplied by 40. That gives us Q equals 7,800 joules of heat absorbed. In other words, to raise the temperature of that half kilogram copper block by 40 degrees Celsius, we need 7.8 times 10 to the power 3 joules of energy. Pretty neat, right? And this simple formula works for everything, from calculating how much energy is needed to heat your kettle to understanding energy changes in spacecraft re-entry. Alright, let's cool things down and wrap it up. Specific heat capacity tells us how much energy a material can absorb before its temperature changes, a direct link between heat and molecular motion. We saw that it depends on the nature of the material and that water, with its huge specific heat, acts as Earth's climate regulator, moderating ocean and atmospheric temperatures. For gases, we learned that heat capacity differs depending on whether the gas is allowed to expand, giving us C sub P and C sub V. We also explored calorimetry, the art of measuring heat exchange using the equation M1S1 open bracket T1 minus T close bracket equals M2S2 open bracket T minus T2 close bracket. Finally, remember the key equation that ties it all together. Q equals M multiplied by S multiplied by delta T, and for moles, Q equals N multiplied by C multiplied by delta T. Specific heat capacity is the bridge between microscopic energy of molecules and macroscopic heat flow. It's what makes a metal spoon burn your hand faster than a wooden one. I hope this session heated up your understanding without overheating your brain. See you in the next class, where we'll explore latent heat and the hidden energy of phase changes. Till then, stay curious, stay cool, and keep your physics temperature just right.